Hi everybody, welcome to the review for the third midterm. It will be in week 13, right before Thanksgiving. Same protocols as before, in class, on a sheet of paper, supplied with an equation sheet, and Monday, Wednesday and Friday on each of the events. The material covered is the stuff from week 8, which is conservation of energy, the stuff from week 9, which for you was online, which is dimensional analysis, and weeks 10 and 11 for pipe flow, except not for pipe networks, which was, I guess, the third of the classes in week 11. The 3 questions relate to the first topic of conservation of energy. There's always a question on Buckingham Pi and using that to define similitude in systems and make connections between models and prototype behaviors. And finally, one on pipe flow, including something on manometry as well. And manometry was from much earlier in your fluids career. So the materials that we have dealt with the energy equation. The energy equation is just Bernoulli, but with an additional part that's added in to accommodate for head losses. The first time Bernoulli does is an inviscid system, so it doesn't allow for any frictional losses in the system. You can often think of it as being written between upstream and downstream in terms of the upstream Bernoulli, the downstream Bernoulli. It has to be written in that order for the signs of the head losses, which are always positive, and the signs for the pump heads, which are positive for pumping and negative for a turbine, for that sign convention to be correct. Certainly we look in this case, I guess these velocities would be 0 if they're written on the top of the large reservoir, and if they're written inside the pump, they'd actually be finite, as they're shown here. But if you have an example where you have 2 reservoirs upstream and downstream that are large volumes, then you can remove those velocity terms by writing the equations on the surface where the pressures are 0 and the velocities are 0. And so you just remove the first 2 terms on each side, and you can concentrate on the remainders. The velocities that are used in the head loss, which are here, are average velocities within the conduit. And so the fact that you'd have 0 velocities at the upstream, this velocity would be in the linking pipe that you're flowing along. If the velocities are 0, yes, okay, that's making the same point here. Upstream and downstream velocities may be 0, but the average velocity in the pipe might not be, and you have to be able to account for that. If you have more unknowns in your Bernoulli equation than 2, than 1 actually, then you need to be able to constrain it somewhere else. So you can use the continuity relationship in that the inflowing volume and the outflowing volume rates are the same. So you can do this if you have 2 unknowns in your Bernoulli equation. The sign conventions are always positive for input, negative for pump. It defines the pump head. This is in units of length, so it would be meters in our particular case. And this is power, so this is watts, joules per second or Newton meters per second. Mass flow rates, acceleration due to gravity. Mass flow rate is, of course, the product of volumetric flow rate and density. And you can always get volumetric flow rate from the product of volume times the cross-sectional area. Typically, you just rewrite this in terms of power being equal to the pump head multiplied by mass flow rate and gravity, just a rewriting of this equation here. Minor losses are those that are in bends and elbows of flow systems, or filters for that matter, and they're typically defined in the turbulent regime, which has a single value of this loss coefficient, which is not a function of Reynolds number, but is constant. Major losses are with the length of pipe and the diameter of pipe, and the friction factor, which is a constant at any particular Reynolds number. Friction factors may be constant or may be varying with Reynolds number, depending on whether they're turbulent or laminar, as you know. Those comprise the magnitudes of these. If you have multiple bends or elbows in a system, then you have to work with the sum of the head losses, etc. The parameters that define this are the diameter of the pipe, the velocity, which would define the Reynolds number, the length of the pipe, and the relative roughness on the surface of the pipe, along with the density of the fluid that's flowing and the viscosity of the fluid that's flowing. In the case of major losses and friction factors for pipes, then this can be obtained from the Moody chart. If you need to know that, you'd be given one in your script. Otherwise, you wouldn't need to know it. They show this behavior that the friction factor is a function of Reynolds number. Reynolds number is the average velocity in the pipe multiplied by density and a characteristic dimension. That characteristic dimension for a pipe is typically the diameter and the viscosity of flow. Large Reynolds numbers mean fast flows, and you get this division of two behaviors as you go from laminar behavior to turbulent behavior. And that is the friction factor for laminar behavior is typically a function of a number divided by Reynolds number. It's inversely proportional to Reynolds number. And so you need to know the Reynolds number at which you're flowing to be able to get that magnitude. And in the turbulent regime, for any given relative roughness, you define a friction factor as one of these lines. And then for any value of the Reynolds number past the threshold into turbulence, the friction factor would always be constant. These individual lines vary with relative roughness. These are values for rough pipes. These are values for smooth pipes. And ultimately it asymptotes to a value which is for an infinitely smooth pipe, a glass pipe if you like. It's important to realize that the friction factors are a function of Reynolds number in the laminar regime. They're not a function of Reynolds number in the turbulent regime, but they are a function of the relative roughness. We talked about solutions for pipe flows going into types 1, 2, and 3, by far the easiest one. And actually the one in this test is a type 1. It's where you're given a magnitude of a velocity or a flow rate, and from that flow rate and the pipe size you can define a Reynolds number, from the Reynolds number being equal to the velocity times the diameter times the density of the fluid divided by the viscosity. So you can define Reynolds number. If you know Reynolds number, you can define a friction factor. If it's turbulent flow, or if it's a large Reynolds number, then the friction factor, at least for rough pipes, is constant because you're on this line here. And then you can use that to determine the head losses in the system for major losses, and also the head losses in the system for minor losses, such as in elbows and fittings. This is always the average velocity in the pipe or in the fitting. Okay. Always a Buckingham Pi problem for dimensional analysis. We can define behavior in terms of mass, length, and time, where we define the number of these variables that we have in any problem as the sum of the number we have. So if you have mass, length, and time, k is 3. We have a number of variables that describe the system. They might be pipe diameter, density, velocity, length, and viscosity. If we have all those in a problem, then we have 5 variables. And so the number of non-dimensional parameters, pi groups, that you have is always the number of variables minus the number of MLT that are included in those variables. In this case, we have length for sure, we have mass for sure, and we have time for sure. So we have 3 in this particular case. So this system, should it be defined, would have 5 minus 3 pi groups, which is 2. Typically, you define dependent variables, or you define repeating variables, should I say, not dependent variables, which would be the same in each of the pi groups. and the one remaining variable, which isn't included in those, is used in each of the pi groups, individual pi groups. Typically you're given these because if you don't use a specific repeating and non-repeating variables, you end up with potentially different pi groups, and so that's ambiguous. So you'd always be given the parameters to use in terms of the repeating variables and the non-repeating variables. The goal of Buckingham Pi is to be able to define the non-dimensional pi group as a function of the non-repeating variables and the variables to the power A, B, or C. It's just a recipe. So you can go through defining the magnitudes of each of the mass, length, and time in each of these parameters to define exactly what A, B, and C are. And once you have A, B, and C, then you can resubstitute back into this group to get the pi group. You can do that for a second one exactly the same way, again with these repeating variables. And as a result of that, you'd find out what your pi 1 and pi 2 values are. If you know what those are, then for similitude, which means that if everything's the same in your model and prototype, then the parameters for pi 1 would be the same. And if the parameters for pi 1 are the same, then pi 2 are also equivalent between the prototype and the model. So often pi 1 might be Reynolds number, often pi 2 might be the Euler number, in which case for flow at a given Reynolds number, you can always calculate the forces that are acting on a cycle, a structure. If you have 3 pi groups, then you'd have an extra relationship such as this. So if you have a value for the pi 3 being the same, then you can always link these two together to get the values of the prototype versus the values you have defined for the model where you've done the experiments. Similitude requires that we have the same behavior defined. There are 3 kinds of behavior we're interested. Geometric similitude is where the model is a scale model, so the length in the model has to equal the length in the prototype, and that has to be the same for all features, wingspan, diameters, etc. in a model. Kinematic similitude is where the Reynolds numbers match between the model and prototype, and so therefore the flow regime is exactly the same in each one. And if those cases are met, then you can calculate the forces in a structure by realizing that if these 2 cases are met, then the point where they meet would give you a value of the Euler's numbers being the same. And if that's the same, then you can use, for instance, the pressure in the model to calculate the pressure in the prototype, because you know that these ratios are the same. Okay, so that's dimensional analysis. Often in using dimensional analysis, you need to work out what the units are to be able to define the mass, length, and time exponents that are used. And so you can always do that if you know what the properties are, realizing that Pascal is a Newton per meter squared. A Newton is the force required to give a kilogram an acceleration of 1 meter per second squared, for instance. And if you can break it into these components, you can always define what the exponents would be of mass, length, and time. Likewise for pressure, you can do the same thing. Some items might not have all of mass, length, and time present, such as rotational rates in radians per second. Radians are non-dimensional, but seconds definitely are. So this would be not that. This would be t to the power 1, time to the power 1. Let me actually write that properly. And also, you need to remember how to do manometry. Manometry, we have some rules which define behavior. You can always work your way from one location to others. So if you start at this location, you can work your way around a circuit according to the rules. The rules are if you move horizontally and it's a simply connected pathway through 2 points like this, these by definition have to have the same pressures, because pressure as you go horizontally doesn't change. If you go up, you subtract pressures. If you go down, you add pressures. If it's evacuated, don't need to know that, but it's equal to the vapor pressure. And typically gases have unit weights which are perhaps 1,000th of those of liquids, and so you can typically ignore those if you're going up if you have liquids in your system. And if you need to go from this point here to this point here, all you have to do is take the pressure at this point, add the change in pressure as you go down a length L01 to this point here, multiplied by the unit weight of the blue fluid, which is this, you're going down. If you're going to this point here, you could just realize that they're the same pressure, or you could go down and subtract the length times the unit weight for the green fluid, and then go up, add the unit weight for the green fluid and go up and subtract that magnitude. These two, of course, will cancel out from each other, and then you find yourself at this location, and that is the pressure at point P2. And yeah, so you can move between those quite straightforwardly. Of course, the difference in pressures between P1 and P2 would be 0 because they're on the same fluid. And that's it, I think, right? So good luck with your work on the midterm.